Test go. Alright, I don't see anybody scowling here. The TAs will get those back to you very soon. And also, before we get started, I want to mention something about the homework. There's a question in there where I have these random variables, and sigma squared is the variance of xi, and I'm letting sigma squared in one of the questions depend on them, change to them. And somebody asked the question, how can it change to them? Well, technically, I didn't want to draw too much attention to it, but if I say I have n observations for a distribution P, I could actually let the distribution change with n. And that's what we're doing in that question. So it might seem odd that we're letting it change with n, but actually it's something that turns out you'll see to be quite common. It goes up quite a bit. So don't let it bother you that the variance is changing with n. It's fine. The way to think about it again is that this is maybe a different distribution for each n. But it's still an IID sample for some distribution. The only thing that's changing is you can think of sigma squared and then depend on that. So don't let it freak you out. There's nothing weird going on. Okay, so it's pretty straightforward.
So it's confusing me that you say it's still an IID. I believe it's still independent, but it's not identical.
Yes, they're all drawn from the same. Now, when I talk about a sample size n plus 1, I might be talking about a different distribution. So the way to really think about it, I didn't want to get too much. This is called triangular array asymptotics, where you have one observation, then you have two observations, then you have three observations, then you have four observations. Don't think of them as the same sequence. Think of it as a different sequence at each end. So and each one is drawn from a possible different sequence. Each row is IID. But don't think about it too much. Just crank away. It is a subtlety, but you can pretty much ignore it. Now, for those of you who came in late, the reason why you want to get here on time is because I give the most important, critical information about assignments and tests in the first 60 seconds of class. And I'm not kidding. All right. So we're going to continue talking about where are we? Lecture note 2, uniform bounds. Just before we get going, any questions? Is everybody off the waiting list? Who wants to be? If not, you should talk to Paige in the statistics department, but it should all be cleared up. All right, where did we leave off? Suppose I have some sample space. Here's some event A. And imagine I draw a random variable. The random variable will fall into A with some unknown probability, P of A, the probability X falls in A. And if I ask you, what is that probability? You don't know. But if you have n IID observations, you might just look at the empirical probability, P sub NA, just the fraction of observations that fell into that's the indicator. And if I ask you, how far is this from this? Well, again, that's just Hooftings inequality, right? Because these are coin flips. You either succeeded, it fell in, or it failed, it fell in. It's a Hooftings situation. And we know that the probability that P n of A and P of A is bigger than epsilon satisfies this bound, which is going to 0 very quickly. Okay, but the question we were starting to address for the test was, what if I don't want to just talk about one particular thing, but a whole bunch of things simultaneously? And what we saw was guaranteeing that this is small for one thing at a time doesn't mean that it's uniformly small. What we'd really like to say is that the probability that the maximum over some set of And because we're taking the maximum over a whole bunch of different probabilities given simultaneously, it's a bit trickier. It's not enough to do it for each one separately. And so that's uniform. That's what we call a uniform bound, uniform over the set. And I motivated on Wednesday's class why in various places we're interested in bounds like that. What's going to end up happening is we're going to end up with a bound just like Hoeking's inequality, but there'll be something in front which somehow measures how complicated the number of things is that we're looking at. Some sort of complexity there. So let's do this. First of all, let's do a simple case, which is suppose I had some finite number of events. So I'm going to go like this. And suppose I'd like to estimate the probability of each of these events, but I want to get them all close. So this is the simplest situation where instead of dealing with one thing, we're dealing with capital N, which is still finite. Okay? Then what we can do is say the probability of the maximum following now. What we're really looking at is, if you think about, if you let Bj be the event that this one is off by at least epsilon. So the probability the maximum difference is bigger than epsilon. You're really looking at events of this form. This is just saying that the empirical probability of the jth one minus the 2 probability is bigger than epsilon. Another way to say this is that the only way the maximum is going to be bigger than epsilon is that that's identical to saying at least one of these events is true. At least one of them is bigger than epsilon. And so this is really the probability that at least one of those events is true. And now we use a very simple thing. These events are not disjoint, but you know that we always have, so we can't write P of union is equal to the sum of the P's, but we always have it as less than or equal to. So I can always write that this is less than, this is called the union bound. So that's called the union bound. Probability of the union is less than or equal to the sum. And what is this? This is just the sum of, this is the probability that the jth one epsilon. Now this is reduced it to a single event. This is where I can apply Hoeking's inequality. So I can apply Hoeking's inequality, and then if I sum, well that's just, it's the same number summed up n times. So this is less than or equal to 2n times e to the epsilon squared. So you can see even if capital N is pretty big, this will still go to 0 pretty quickly. Why? Because this part is going to 0 very fast. And notice that this is just Hoeking's inequality with an extra term in front of it, in this case just the number of events. And that you can think of that as sort of the Hoeking thing times, what is this? This is like a measure of the complexity of this class of events, just namely how many of them are. So that's the simplest way to control, that's the simplest way to control this probability. That gives us uniform control over this whole thing. But you can see there's a limitation to this, because what if this class was infinite? Well, that's not going to help us very much. We're going to have an infinity here. So what we really want is a more sophisticated way. We really want a more sophisticated way to control this probability other than just counting. Because that's not going to work with an infinite number of things. What's an example of an infinite number of sets? Let's suppose A was the set of all disks. Or, how do you spell disk? I always forget if it's here. Disks on R2. I don't know if that's spelled correctly. So in other words, sets like this. various sets like this, you can just think of all the disks on R2. And for every disk, you can compute the proportion of points that fall in it. And now the question is, how close is that proportion to the true probability? In other words, I want to know Pn of A minus P of A. What's the probability that, what's the maximum error? What's the probability that the maximum error is going to be? Well, I can't use this technique because there's a lot of disks, certainly not finitely many. So we need some better way to control this probability other than just counting. And so the trick here, or one of the tricks, the most elementary trick is to use, it's called shattering and the DC dimension. Some of you will come across it before, some of you won't. So I'll assume you haven't seen it before, and we'll do it from scratch. And it works like this. So what we're going to do, you're going to give me a class of sets that we're interested in. And now we're going to measure, in some sense, the complexity of this class of sets, possibly an infinite set. Now, there's many ways of doing it, but the simplest one is this idea of shattering and DC dimension. So we're going to do that one. And remember, this could take many different forms. I could give you, A could be the set of all sets on the real line of the form minus infinity up to a real number t, as t varies on the real line. In other words, the set of all half intervals on the real line. That's exactly what we're computing when we compute a CDF. The CDF is just computing the probability of all those things. Or it could be the set of all disks. Or it could be the set of all rectangles. It could be anything you can imagine. The set of all half spaces. Whatever. It's just some collection of sets. So here's how we're going to measure how complex is this. We're going to imagine, first of all, taking an arbitrary finite set. Now remember, I might be working on, like in this case, I'm working on the real line. In this case, I'm working on R2. So we have to have already decided what set, what's the basic set we're working over. What's the sample space? And this set F will just be an arbitrary finite set in this space. So in this case, it would be some arbitrary finite set in R2. So this is it. Some arbitrary set. All right. Now what I'm going to start to do is so you've given me I've just picked an arbitrary finite set, but I also have this class of sets that we're interested in. What I can do is take any set from here and intersect it with this finite set. So let's do it. Let's take a disk here and intersect it. Maybe I'll take this disk. What do I get? I get a subset of F, right? So every time I take A intersect F, I'm going to get some, let's call that G. That's going to be some subset of the original set F. Okay. And now you can see as I try different disks and put them on here, I'm going to pick out different subsets. That's called picking out subsets. So what we do is, the key thing is this. This is the number of subsets that are picked out. What do I mean by that? You may not be able to get every possible subset. In fact, let's do this simpler example here. Let's take these things. So now I'm going to have to pick a set F, an arbitrary set F. Let's take F to be just, I don't know, let's say these 2 points. There's my finite set. Let's consider all the infinite one-sided intervals of this form. So first of all, let's think about the finite set F, which consists of this point, this point. How many subsets does that have? How many possible subsets can I extract from that? Those 2 things? Well, 4, right? I could get the empty set. I could get the whole set. I could get this singleton and this singleton. Now let's ask if I can pick out, let's actually give this a name, x1 and x2. Let's list the subsets. So I can do the empty set, I can get x1, x2, x1, x2. These are the g's, which are subsets of that. And let's see if I can get those by using this target class A. Well, if I take any interval that goes from minus infinity up to here, and I take the intersection with this, I get the empty set. So yes, I can pick out the empty set. How about the whole subset? Well, if I take any set A that goes from minus infinity up to here, and I take the intersection, I get back x1, x2, so I can get that one. If I pick any t here, and take minus infinity up to t, take that set, intersect it with the finite set, I get back x1. But can I ever get x2 alone? No. Right? If I try to move this over and pick out x2, I'll also get x1. So what you can see is the collection of subsets that I can pick out is, it might be all of them, it depends, but it might not be. Okay, and the number of sets that I can pick out, yes, but we did that for one particular set f of a given size n. Now imagine doing that for any set of size n. So what Sn is, this is called the shattering number. This is the maximum over all finite sets of size n. I'll write it like this. So what you do, you take an arbitrary set of size n, and you say, how many subsets can I pick out, and what's the biggest I can make that? That's now just going to depend on n, and that's the shattering number. So let's think about this shattering number. In fact, let's continue with this example. This is actually a good example because it's really simple. So continuing with that example, what I'm going to do is put down here a little table, n, which is 0, 1, 2, 3. I'm also going to write 2 to the n, because, why do I care about the number 2 to the n? Well, we know that the number of subsets of a finite set is 2 to the n, right? That's as many subsets as there are. So the biggest S of n could possibly be is 2 to the n. It's somewhere between 0 and 2 to the n. This is the maximum. So this is 1, 2, 4, 8, and so on. Now I'm going to write down the actual shattering number. So let's continue with this example. Well, the empty set is kind of trivial. But if we consider an arbitrary set with a single point, again, it's kind of trivial. There's two possible subsets, the empty set or that thing, and no matter, it doesn't matter where I put this point. If I consider all these half intervals, I can always pick out both of them. So in particular, the maximum is 2. I can always get 2. But we already saw that in the case of 2 points, there was 4 potential sets, but I could only pick out 3 of them. Now the question we have to ask is though, is I have to take the maximum over all sets of size 3, but of size 2, but you can see that the fact that I could only pick out 3 of these sets didn't depend on x1 and x2. I could have moved them anywhere and this would still be true. So even if I take the maximum over all possible 2-point sets, you can see that the shattering number is 3. What if I pick an arbitrary 3-point set? What is the shattering number? How many subsets? So there's the maximum number is 8. Can I get all 8? No. Let's think. I can get the empty set. Yes. Let's see. I can get x1. Yes. Can I get x2? No. x3? No. How about x1, x2? Yes. How about x1, x3? No. x2, x3? No. And then x1, x2, x3? Yes. And so, there's 8 potential subsets, but I can only get 1, 2, 3, 4, And most importantly, again, it didn't depend on the choice of the 3-point set. You can see that the logic didn't depend on where I put them. So the maximum over all 3-point sets is this. This is the measure of complexity of this class of sets, is the shattering. The fact that it doesn't always equal 2 to the n is showing you that there's some restriction here on this class of sets. And that's measuring the complexity. Somehow, the fact that this is not always 2 to the n, at least not in this example, is telling you this class of sets is not as rich as you might think it is. There are actually some classes of sets where this does go up like 2 to the n, where these two columns are the same. Those are much more complex collections of sets. So here's one of the biggest theorems in statistical machine learning due to Batnick and Chervonenkis in the 80s. And we proved this theorem in 702. We're not going to prove it in this class, we're just going to state it. And it's just an extension of Hoeffding's inequality, which says that the probability that the empirical estimate minus the truth, that the maximum of this over the entire class is bigger than epsilon, is less than or equal to 8 times the shattering number times e to the minus n squared over 32. So let's look at this. What this is saying is, this looks a lot like Hoeffding. I mean, Hoeffding had a 2, this has a 32, it doesn't matter so much. There's still the exponential focus here. But the important thing is this. There's the shattering number, which controls, which is sort of saying the bound is this tight, a very complex class. This Sn is somehow potentially increasing with n. It is getting bigger with n. If it's getting bigger with n very rapidly, like it's going up like 2 to the n, we're in a pretty hopeless situation, because if this is like 2 to the n, that's sort of going up exponentially. This is going down exponentially. That doesn't work out so well. So if you have a really complex set of sets here, you might get a poor bound. That doesn't mean it's hopeless, by the way. It just means this technique might not be the right method. But if this is going up with n much slower than this is going down, then we're in a good situation. That's what a lot of classification tends to focus on, that situation. Which raises an important question, which is, so what does this behave like? How do we know what this behaves like? Well, here's an interesting thing. This is the unexpected part. What you saw here was that I put the biggest it could be here, 2 to the n, then we somehow computed this Sn. It's not obvious how to always compute that, but let's assume we can always compute this. And what you notice is that it was equal to 2 to the n for a while, then it started being less than 2 to the n. So we can draw a graph which explains this situation. I'm going to put on this axis n. And I'm going to plot the shattering number. And so keep in mind that it might, we've only done one example. So actually computing these shattering numbers, how do I know what this S of n is? Might be hard. But let's assume somehow we're able to compute it. What I'm going to plot is 2 curves. I'm going to plot the biggest the shattering number can be, which is 2 to the n. So that's this exponential. But what we saw here was sometimes when I look at the shattering number, it follows 2 to the n, and then it was less than 2 to the n. So the shattering number might do something like this. It might be equal to, equal, and then it might be a bit less. Great. So it might be, the shattering number might be equal to 2 to the n, so then it might start being less than 2 to the n. And it's easy to check that once it's less than 2 to the n, it stays less than 2 to the n. And there's a name for this situation. If this happens, it doesn't have to happen. If this happens, this number, the largest number where it's equal to, is called the BC dimension. So the BC dimension, you see, is the largest and such that the shattering number is equal to 2. That's, again, some measure of the complexity of the class. Something that has a small VC dimension is in some sense a smaller collection of sets. Something with a big VC dimension is a more complicated collection of sets. Now, if I tell you, okay, it's equal to 2 to the n, and then it's less than this over here, but we still don't know much about how does it behave after this. The remarkable thing is this thing that's called Sauer's lemma, which says that once, this is amazing, this is going up exponentially until the VC dimension, then it only increases polynomial after that. There's nothing in between. It's a phase change. So what this says is that, suppose the VC dimension is finite. What I mean by finite is, it's possible this never happens. It just keeps going up and up and up and up, in which case we say it is an infinite VC dimension. So let's suppose there is some place where it starts dropping below. That's finite VC dimension. And then for all r den, whenever n is bigger than this finite number d, remember d is fixed, then the shattering number is less than or equal to n plus 1 to the d. So what's happening is that the shattering number goes up exponentially, like 2 to the n, until you hit the VC dimension, then it becomes like a polynomial, like n to the d, n plus 1 to the d. So what's going to happen in those situations is that when n is large enough, you're going to have the complexity of the class here is growing like n plus 1 to the d. That's going up, but it's only going up as a polynomial. This is going down exponentially. This is going to beat this. This is still going to go to this. That's what's special about these collections with finite VC dimension, is that we have this extension of Hoeffding's inequality. All you have to do is stick this extra term. So this is a very important. Yeah, oh yes.
Sorry, are you saying it grows at a polynomial rate, or that it grows like one particular polynomial?
Particular polynomial, n plus 1 to the d. It's very specific.
Can't it grow faster at the beginning and then become slower? Like, wait, the other way around.
No, it turns out it's a very particular bit. This is it. It's rather remarkable. Now, so again, I'm not going to prove this. This is something we proved in 702, which is that. The other thing is, how do you compute the VC? And that can take, you know, it can be sometimes trivial, it can be sometimes so difficult, but there are still some examples that don't know the VC dimension. So for this class, we're just going to think of it as a dictionary. Whatever class we're interested in, somebody has computed it, and we can just look it up. So, I mean, you should try a few simple examples. Like try the disks in R2 and convince yourself the VC dimension, what is it, 4? I think it's 4 or 5, something like that. In fact, the top of page 5, I put a few of them. So for the set of intervals in real line, the VC dimension is 2. So you should convince yourself of that. That means that you can, that there's a 2-point set that you can shatter. Shatter means pick out every possible subset. So there's a 2-point set you can shatter, but no 3-point set can be shattered by the intervals. And you can see the closed balls have an upper bound is 2d plus 2. The rectangles in RD is 2d and so on. So these things are known for lots and lots and lots of interesting classes. And so we'll just think of it as something we can just look up. And once you know that VC dimension, you know the shattering number, and once you know the shattering number, you have this extension of what's okay, so this is something that will come up in various places for us. And for now, that's really all we want to say about this. It's something we may need in more detail later, and certainly in 702 we need it in more detail. For now, all we need to know for this class is, for a single thing, you use Hoeffding's inequality or one of the other inequalities. For a collection of things, we just use this extension of Hoeffding's inequality, the VC inequality is called. That there are other ways to get these kinds of probability bounds besides the VC method. those come up probably in other courses, not so much in this class. VC stuff is sort of the easiest ones. Now, things with VC, finite VC dimension, you can think of as, they might have infinitely many sets in them, but they're still pretty simple classes. That's what we're doing. In some sense, it's like saying they're finite dimensional sets.
What does VC stands for?
Gapnik-Chervonenkis. Gapnik-Chervonenkis.
Oh, okay.
Those are the two Russian guys who proved the original theorem. Okay, so we'll return to this as needed. But you should at least take, say, the intervals on the real line or the balls in R2 and convince yourself, convince yourself that you know how to figure out DC dimensions in those simple cases. And with that, we're ready to move on to the next section. Any questions? Okay, so we're ready to move on to the fourth set of lecture notes. This is chapter 5 in the book. And this is about convergence theory. Probably one of the most important parts of probability theory, and certainly a critical aspect of probability theory that gets used in statistics and machine learning all the time. And it's answering the question, what happens as I gather more and more data? So as we gather more and more data, which is presumably what we want to do, we want to ask how our various probabilities behave. And the two big results that we'll eventually talk about are the law of large numbers and the central limit theorem. And they're pretty precise descriptions of how various random variables behave as we get more and more data. So just to back up a bit and set the stage, we're going to be dealing with sequences of random variables. Some distribution or some CDF. We're typically going to be looking, though, at not the original sequence, but some statistic computed from these. Okay, so in other words, I'm going to compute some functions, let's call it t-values, this. And it's usually this thing that I'm interested in knowing what happens when n gets larger and larger. So examples are the sample mean. So that's a function of the first n observations. If I think of this as a sequence of random variables, you can see these are not IID because they overlap. They're not independent. And so the original sequence, right, the sequence of statistics, statistics is just a function of the data, may not be IID. Okay. And another example, of course, would be sample variance, and there's lots of other examples. For your convenience, at the first page, I reviewed a few properties of these things, but they're just there to remind you, you already know that. But now, again, let's think a little bit more abstractly. I've got this sequence, so actually let's write it this way. I've got the original sequence, and it might be IID, but now I'm always computing something from the first n data points. So now I have a new sequence, and just think again of the sample average. This is an arbitrary sequence of random variables now. So what we're about to talk about is an arbitrary sequence. Think of them as x bars, so they're not necessarily independent. All these notions of convergence I'm about to talk about don't depend on IID. And what we want to talk about is what does it mean for this sequence of random variables to converge? So in calculus, convergence is pretty easy. It's all like delta epsilon stuff. For random variables, it's a little more complicated because these things are random. I can't talk about the limit because in the usual sense, because it's a random thing. Yes?
Subscript n with g.
You're right. Technically, I should write. All right. So what we're going to do is define many different types of convergence. Now, if you haven't seen any of this before, I'm going to warn you that at first it's a bit overwhelming, it's going to seem a bit confusing, but then we're going to spend the next few lectures putting it all together into some sort of coherent picture, so it all makes sense. So, I'm going to just write the definitions down, then we're going to spend quite a bit of time doing examples and saying how are these different types of convergence related to each other and so on. So the first one is called almost sure convergence. We have xn is a sequence of random variables, and we say that it converges almost surely to another random variable x. That's the notation. What does it mean? It means that if actually, let's just let's do the simpler one. We can talk about almost sure convergence to a random variable, but we can also talk about almost sure convergence to a constant. And it's really the second one that we care most about. Let me just focus on that one. And all it means is if I look at is the limit of xn is n goes to infinity equal to c. This is a random event. This is random, so it's not like calculus, but I can say if the probability of this event is 1, then we say that xn converges to the constant almost sure. Okay. Now comes the second one, and this is number 2 in your notes. You can both read. So xn converges to a random variable x in probability. What does that mean? It means that for every epsilon greater than 0, the probability that the difference of these random variables is bigger than epsilon goes to 0, as n goes to infinity. And again, there's another version, which is more commonly used, which is that xn converges in probability not to a random variable, but to a constant. So that one's a bit easier to understand. For every epsilon greater than 0, the probability that xn minus the constant greater than epsilon converges to 0. So how do we picture this? The picture you want to have in your mind is this. xn is some distribution. And what this is saying is, if I put an epsilon, no matter how small, and I compute the probability outside this region, when n is large, that probability is getting very small. So in other words, as n gets large, this distribution is getting more and more squished towards 0. In fact, we've already seen this definition. We just gave it a different name. Namely, xn minus c is little op. Little op1 is actually convergence of roughly. That was exactly how we defined convergence of op1. Little op. The picture to have in your mind again is somebody tells you the distribution of xn, you draw it. Then they tell you the distribution of x n plus 1. You go out and you keep looking at these pictures, and they're getting mushed here towards 0. You can't say that the random variable itself is at 0. It's just that most of its probability is 0. This is a very important. I'm going to tell you. I'm giving you lots of definitions, but 2 of them are really important. This one's purchasing probability is a central concept. And I know that probably seems a lot like almost sure convergence. But I'm going to show you examples later where that they're not actually perfect. All right, let's continue the barrage of definitions, get them out of the way. There's 2 more. And in fact, there's a lot more than 2 more, but I'm only going to do 2 more.
Does almost sure convergence imply probability?
It does, but we'll get to that later. Yeah. Convergence and quadratic mean. So xn converges to x in quadratic mean, or some people say in L2, if the expected value of xn minus x squared goes to 0. say xn converges to quadratic mean for a constant, this means that the expected value of xn minus c squared goes to 0 as n goes to infinity. And finally, convergence and distribution. X and convergence and distribution. Now there's two common ways to write this. One of them is with a squiggly arrow, but some people write like this, with a D for distribution. And what it means basically is that the CDF of this converges to the CDF of this. Okay, so what that means is, if I denote, let's say the CDF of this is Fn and the CDF of this is F, it means that this converges to this. There's one catch, very important catch, which is we only require this to hold at points where F is continuous. At all t, F is continuous. And I'll show you by example why we want to make that exception for this. And this is the other really important one. Convergence and distribution and convergence and probability are the two central things. Yes?
So you're saying only when the CDF is continuous?
No. We're requiring the limit of Fn t to be equal to f of t at every point t for which f is continuous.
What if that is not?
It's, then it would be, I guess, what would we say then? It would be convergent by some sort of default or something like that. That would be really interesting. But we're not going to deal with anything like that. All right. So, again, this can be pretty confusing because there's so many different definitions and so on. Actually, let me draw a picture right now to tell you how they relate, and then we'll go back and fill in the details. And by the way, if you look at a book of probability theory, you'll see there's many other types of convergence too. The story's kind of complicated, but I'm going to just give you this. This is a good picture to have in mind. Almost sure convergence implies convergence probability. Convergence probability implies convergence distribution. Convergence of quadratic mean implies convergence of probability. In general, the reverse implication is not true. Now, the two we care about are this one and this one. This is a much more subtle type of convergence, and to be honest, I only mentioned it for completeness. We don't really deal with it in this class. And the only reason why I introduced this one is because sometimes we're going to want to prove something is converging in probability, and sometimes it's actually going to be easier to prove this, and then use the fact that this implies this. So it's really just a tool for us to get a convergence of probability. It's really convergence of probability and convergence of distribution that we really care about. So, let's see. Let me just pause. I'm going to hopefully make all these much clearer now because we're going to prove which things imply which things, which things don't imply which things, with examples. Let me see if there's any questions about the answer definitions. Yeah.
So these all apply to both discrete and continuous?
Yeah. Right, this is not saying anything about whether it's discrete, continuous, independent, right? It's the general definition. Okay, no other questions? So let's start playing around with some of these definitions. So as I say, almost sure convergence, not so important for this course. And so I'm going to, so Theorem 3 is very short, but I'm not going to go through it. It shows you that convergence and probability does not imply almost for convergence. Basically, by construction, it shows you an example of something which converges and probability does not converge almost surely. I'm not going to cover it because I consider, again, the almost sure not critical in this course. If you're curious, it's there. If you're not, you can see it. It is kind of fun to look at that example, but I want to focus on the ones that are a little bit more germane for this course. So now I want to show you, let's say, example 4, which looks at some of the different types of convergence. Here's example 4. I'm going to consider the following sequence of random variables. I'm going to take xn to be a normal, with mean 0 and variance 1 over n. So very small variance. When n is large, this is a very small variance. Now intuitively, this is sort of concentrating around 0. So in some sense, this is converging to 0. Let's just show that it's converging to 0. Let's start with let's show that it converges to 0 in distribution first. But what do I need to say that it converges to 0 in distribution first? Convergence in distribution is what convergence of random variables. So is there a random variable which is always 0? Sure. Right? Let's define the following CDF. Let me use the same notation I used here. Let's have one. Define one. So, imagine a random variable which is always equal to 0. Just always 0. What does its CDF look like? Well, it's just 0 here, and then it pops up to 1. It's always equal to 1, so it puts all of 0, so it puts all its mass at 0. So the probability that getting a number, I got that right? Did I reverse that? No, right. Yes, if I draw x randomly, right, if I draw x randomly, I get a 0. So the probability that's less than any number here is 0. But if I draw a number over here, the probability that's less than or equal to that is 1. And remember, it's less than or equal to, so it's right continuous. So the probability that it's less than or equal to 0 is 1. There's a jump there. Now, let's look at so this, by the way, let's write down the CDF. This CDF, this deterministic CDF, I want to think of it that way, is 0 for t plus 0 and 1 for t. I want to show that this CDF for this converges to this CDF. So Fn of t is the probability that x of n is less than t. And the way I did this in the notes was I just multiplied both sides by root n. Because what is the distribution? It's called as z. What is the distribution of root n xn? It's a standard normal 0, 1. So this is just the probability of standard normal. So let's consider two cases. Let's take positive t. What's the probability z is less than this? So what happens when this is positive? This is going to infinity. The probability less than this is going to what? Which is exactly what we want, right? That is f of t is equal to 1, very positive. That's the t positive. If I take t negative, then I have the probability that z is less than root n of t. This is negative, this is going to minus infinity. The probability that z is less than something going to minus infinity is obviously getting smaller and smaller. That's going to 0. But that's what we want. That's also equal to f. So for every positive t and every negative t, we have that fn of t is going to f of t. What happens at 0 though? Let's actually ask for any n, what is this? What's the probability that xn is evaluated at 0? What's the probability that a normal doesn't go to 0? It's a half, right? For every n. This has got mean 0. So this is not converging to this at 0. This is equal to 1, and this is equal to a half. Does that matter? No. The definition of convergence distribution is it has to converge, fn has to converge to fn at all points where f is continuous. But if this continuous at 0, that means we ignore 0. This is why we have that exception, because for this to make sense, we would certainly want to say that this normal distribution is converging a distribution to a point mass of 0, to a distribution that's deterministically equal to 0. But to do that, we have to exclude the discontinuity. So now we have proved that xn is converging in distribution to x, where x here again is a random variable which is always equal to 0. Or we could just write it like this. Xn converges to a random 0 there. That really means a random variable which is always equal. But the way to picture it is, if I drew the CDF to this normal, it's going to look like this. It's always going to pass through a half here, but it's going to get steeper and steeper. And you can see it's getting very close to that CDF. Okay, so that's where we'll leave off. What we'll do is we're going to do more examples like this. Give you a feeling of this. Then we're going to prove formally all of the implications, which ones imply which ones, but also that the reverse implications are false. And hopefully you'll start to develop more and more intuition here about what different convergence means. Any questions? Here we go.